Hi everyone. In this video, I'm going to be demonstrating how to test a full structural equation model using Lavaan in RStudio. And the example that I'm drawing from is from Kline's 2016 text on principles and practices of structural equation modeling. And in particular, the example comes from pages 341 through 348 if you want to look that up. So the model that we're testing right here basically involves four latent variables. We've got constructive thinking, subjective well-being, dysfunctional thinking, and job satisfaction right here. And the boxes that you see in this model, these are measured variables. And so basically we have data on those variables, and we're using these variables as indicators of those latent constructs. So you'll notice that we have arrows that are pointing from each factor to these boxes right here. And the idea behind this is that these measured variables are serving as indicators of the construct. So in other words, they're reflecting the construct. So we have beliefs, self-talk, and imagery serving as latent are serving as indicators of constructive thinking. We've got perform one, perform two, and perform and approval down here serving as indicators of dysfunctional thinking. We've got happy, we've got mood one and mood two serving as indicators of subjective well-being. And then we've got work one, work two, and work three serving as indicators of job satisfaction. So in terms of when we talk about the relationship between the latent variables and their respective indicators, we're essentially referring to the measurement portion of our model. There's another aspect to this model as well, and that's the aspect that we're really mostly interested in testing, and that is the structural portion of the model. And the structural portion of the model reflects our conceptualization about the causal relationships among these latent variables. So you'll see right here we've got constructive thinking being proposed as being a causal antecedent of subjective well-being. We've got dysfunctional constructive thinking proposed as a causal factor in terms of predicting dysfunctional thinking down there. We've got constructive thinking predicting job satisfaction. We've got dysfunctional thinking predicting job satisfaction. And then we've got subjective well-being serving as a predictor of job satisfaction. So basically, just to kind of reiterate, we've got constructive thinking. In terms of prediction of dysfunctional thinking, we only have constructive thinking as a predictor. In terms of subjective well-being, we've got two predictors in the form of constructive thinking and dysfunctional thinking. And then job satisfaction has three predictors in the form of subjective well-being, dysfunctional thinking, and constructive thinking. So in Kline's discussion, he starts out by testing essentially three measurement models. And so the idea at that point, when you're doing structural equation modeling and you have latent variables in your model, typically that process proceeds in a two-step fashion. It begins with testing a measurement model with the idea of trying to determine if the model does if the indicators that you have in your model, if they're serving as good measures of the latent constructs. And so you don't want to have a measurement model that fits the data poorly, because that's going to basically indicate that you're not doing a good job of measuring your latent constructs. And so we start off there, and then if we find that we have a decent fitting measurement model and everything is kind of conceptually holding up, then in that case, then we specify the structural model. So the first part of testing a full structural equation model typically begins with a measurement model, evaluating that measurement model to make sure that the observed variables are serving as reasonable indicators of their latent constructs. And then the second step, if the first step holds up and we have a good fitting measurement model, then we proceed to specifying the structural relations among the latent variables. And just so you know, the process of testing the measurement model involves essentially confirmatory factor analysis. So we're starting off with a confirmatory factor analysis, and then we proceed to adding the structural relations and then testing the full structural model. So in Kline's discussion of the testing of the measurement model, he actually provides an overview of 3 different measurement models. And what we're going to do in this particular video is we're just going to start with the 3rd model. We're just going to start with the model that he decided fits the data best. And so that happens to be a 4-factor model with a correlated error between the happy and mood 2 indicators. So this is the model that he decided on in terms of exhibiting the best fit. And then from there, he began specifying the structural relations and then testing those in the full structural model. So what we're going to do in this video is we're actually going to start by just testing this model. We're not going to test the couple of models that he used before, just in the interest of time. But then after we test this, we're pretty much going to find that it exhibits a good fit. And then we're going to move on to testing the structural model. Now, at this point, I want to mention that the data for this particular analysis is provided in a summary form on page 342 of his book. Basically, he's got correlations, standard deviations, and means for the variables. So we don't have the raw data to work from. And so what we're going to need to do is to input this data into Lavaan and essentially convert the correlation matrix and standard deviations into a covariance matrix, which is then going to serve as our input into Lavaan when we're estimating the model parameters. So what I'm going to do is actually open up a text file right here. And we'll take a quick look at it. Actually, before I do that, let's go ahead and look at RStudio. Here's RStudio right here. And what I'm going to do is I'm going to walk through this text file, and I'm going to basically be copying and pasting into RStudio because, quite frankly, there's a lot of code that's involved right here. And I just find that trying to type things directly into RStudio, or R for that matter, can oftentimes lead to errors. And so it's just a lot of times it's easier just to copy, to type your syntax into a text editor of some sort, and then copy and paste it into RStudio. It just makes things a lot easier. Not to mention that you can keep the text file as sort of documentation of what you did, so you can actually come back to it later if you wanted to. So what we're going to do in this particular demonstration, we're going to start out by inputting that correlation matrix in and standard deviations, and we're going to create our covariance matrix, and then from there we'll run our models. So the first thing that we have to do, though, is in order to do all this, we need to use the library function to call up Lavaan. And I'm going to go ahead and say use the library function to call up this SEM plot, that package that you see right here as well. We're not going to be using that package until much later, but we might as well go ahead and open it up. So the package is SEM plot with a capital P. So don't let that don't forget about that. So at any rate, what I'm going to do is go ahead and copy these and paste them in this part of the syntax in, so that now both of those are active in memory and they're ready to go. So we can use the functions associated with both of these packages. Just as a friendly reminder, if you don't already have the packages installed, then you can't use the library function to call them up. So if you haven't already installed them, you're going to need to make sure to do that. So what I've done in the text file, and I'll make this available to you, is to I kind of go through and I add comments and everything just to kind of describe what's happening as we go along. So you can see right here, a comment starts with a £, and this is the first comment right here. And so in terms of this process of creating our covariance matrix, I started out just by saying, all right, we're going to create the covariance matrix as usual in Lavaan. We're going to, and so what happens is that in Lavaan, when you are entering the summary covariance matrix, you're basically entering in the lower triangle, the principal diagonal and lower triangle, and then you're essentially going to instruct Lavaan to copy the values that are below the principal diagonal above the principal diagonal in their respective positions. And what that's going to do is this going to create a full square matrix that that is then used as an input into Lavaan when we're estimating our parameters. So with this right here, what you see down below, this is essentially the process of entering in the data and creating an object that contains the correlation matrix. And because a correlation matrix is essentially a covariance matrix involving standardized variables, the logic still holds. So you'll see right here that I've got up here, I'm creating an object that's called lower. And I've got an arrow pointing to it. So that's just a less than sign followed by a hyphen. And then you'll see I've got an initial single quote. Now, at the end, I've got another single quote. So we're basically entering the correlation matrix between those two single quotes. And I would encourage you when you're entering your correlation matrix to make sure that you have the rows, the columns aligned. Try to be neat and everything, because quite frankly it's really easy to make mistakes if you don't have things well aligned. So it's not a requirement, but this is just my preference, because there's a lot of input right here and it's a real drag to have to go back and try to figure out where you made an error. So doing this kind of helps out. So at any rate, I just kind of started off right here with the first line. I've got a 1 right there, then 0.668, and then a space, a few spaces, and then 1, and then so forth. So that's all there is to it. It's just, as you can see, the data that Kline provided there were a lot of variables that we were working with. So once we've done that, then we need to create a new matrix that is, a fully symmetric matrix. And so down here, I started a new line. I'm creating a new object called core_mat, for lack of a more creative naming. And you'll notice that I've got an arrow pointing to it. And then you'll see we've got this getCov function. And the C in this function is in caps. So everything else is in lowercase. But basically what we're doing is we're using this getCov function right here, and we are going to take our correlation matrix right here that's called lower, and we're going to type it in the first position right here in our syntax. So then following that, I've got a comma, and then I'm typing in the names of the variables. So I'm using the names argument right here, and then I'm setting that equal to C. And the C is basically a concatenate function. And so inside this next set of parentheses right here, I've got the variable names inside quotation marks, and each variable name inside the quotation marks is separated from the others by commas. So you'll see I've got quotation marks work 1, quotation marks, comma, quotation marks work 2, in quotation marks, comma, and so forth, all the way through. Then I've got to close out the C function right here. So I've got an in parenthesis here, and then I've got to close out this getCov function right here with an in parenthesis. So that's why we have 2 in parentheses right here. So once we've done that, you can see right here, I'm just typing in core_mat, which is the name of the object that's going to contain the correlation matrix, the full square matrix, just so I can visualize that matrix. So I'm going to go ahead and just copy all of this and paste it in and hit enter. And so now you can see I've got the full square correlation matrix. So you can see the principal diagonal right here contains the values of 1. So all the way to the last variable over here. And then you can see on the off diagonal, we've got our elements that contains the correlations. So you can see this value right here below the principal diagonal is equivalent to this value above. It's the same correlation. It's just, kind of repositioned in our matrix. Then you can see here's another one right here, 0.635, 0.635. And here's another one, just 0.599. 0.599 right here. So we're essentially just copying the elements below the principal diagonal and putting them above the principal diagonal in this matrix. So now we've got our full correlation matrix. Now we want to convert this correlation matrix into a matrix of covariances. And so that's where we're going to be using, we're also going to have to input standard deviations. So our next step is to create a vector of standard deviations. So I'm creating a new object that I'm calling SDS, that's in lower cases, and then we'll have an arrow, and then we are using that C function again, and we're creating a list of the standard deviations in the order in which these variables are listed right here. So make sure that's the case. So now I've got 0.939 comma 1.017 comma 0.937 comma and so forth. Notice that these values are not inside quotation marks, but these are numeric values, so we enter those directly without quotation marks. So now that I've got a vector of standard deviations, now I need to essentially create the covariance matrix. I've got the correlations and the standard deviations in separate objects now. The first object, the correlations, are contained in this object right here, CorMat. The standard deviations are contained in this object right here. So now we're going to use this core to cov function to translate our correlation and our correlational and standard deviation data into the covariance, a new covariance matrix. So right here, I'm creating a new object that I'm calling CovMat, for lack of a better way of naming it. And you'll see I've got my little arrow pointing to it, and we're using this function core to cov. Okay, so inside the parenthesis, I've typed in CorMat, which is referring to what we created up here, and then SDS, which is what we had referred to with our standard deviations. So now that I've got that, when I type this in, and basically I end up with a covariance matrix, a variance covariance matrix. So I'll go ahead and copy this as well and paste this in so we can look at it. And you can see right here that it looks like I forgot to copy everything because I didn't copy the standard deviation. So let me try that again. Let me copy all of this, and we'll paste it in and enter. And so now we've got the variance covariance matrix. So along the principal diagonal, we have the variances of each of our variables, and along the off diagonals, we have the covariances. And so again, just to show you that the values are shown below and above. Here's the covariance between work 1 and work 2. There's the covariance between work 1 and work 2. Covariance between work 1 and work 3. Covariance between work 1 and work 3, and so forth. So they're the same values. So at this point, now we have a variance covariance matrix that we can input into Lavaan when we're running our structural equation modeling analysis. Now, just to show you too, you can also create a vector of means, and in some cases there might be a need to have means during your structural equation modeling analysis. So I'm just kind of showing you here. This is not really a central focus, but you can see that you can create also a vector of means. This is an object I'm creating, just calling it means. And then I've got a less than sign followed by a hyphen. There's my arrow. Using the C function, and then basically this set of means right here are in the same order as what we had with the standard deviations and what we were inputting into to create our correlation matrix. So at this point, we've got that. We're going to kind of set it aside for right now because there's not really anything else to do. I just have this created so that I'll have it available. But you don't actually have to have a mean vector to run the structural equation model. It's not necessary. Most, really oftentimes we run our analyses using just variances and covariances, and that's going to be okay. That's fine. But again, in some analyses, there might be some reasons why you might want to include a mean vector. And so that's how you would basically create one. So now what we're going to do at this point is we're going to create the measurement portion of our model. So you can see right here is just another comment. And I'm calling this MM3 to refer to the fact that we're going to be using basically the third measurement model that Kline describes. And So that's an object that I'm creating, which is going to be the measurement model. So you'll see we have our arrow followed by a single quotation mark. And so then it also ends with a single quotation mark. So everything in between those two quotation marks is essentially our code for specifying the measurement model. So as you're looking at this, just kind of notice that we've got a job sat. So this is just going to be the name of the job satisfaction factor or latent variable in our model. And you'll notice that I've set it equal to, and also using a tilde right here, to work 1 plus work 2 plus work 3. So keep in mind, when you're running a factor analysis, you specify the factor on the left side. You have the variables, the indicators of that factor specified on the right, separated by plus signs. And then between those two sets of variables, you've got equals sign followed by a tilde. So that's very, very important. So I've got job sat equals and then a tilde, work 1 plus work 2 plus work 3. Then I've got well-being equal sign, tilde sign, followed by happy plus mood 1 plus mood 2. Then dis thinking right here, that's the third factor, equals sign, tilde, then perform 1 plus perform 2 plus approval. Then I've got basically this constructive thinking factor. I'm just calling it, I'm just typed in CONSTITHINK, equal sign, tilde, followed by beliefs plus self-talk plus imagery. And then we had incorporated an error covariance between the happy and mood 2 variables. So I've got just a little comment right here, just saying error covariance. And then I've typed in happy, 2 tildes, and then mood 2. So the tildes, if I have 2 tildes, if I have the same variable on both sides of the tildes, it's just referring to variance of that variable. But if I have 2 variables on the different sides of the tilde, then essentially that's going to compute a covariance between those variables. Now with happy and mood 2, these variables happen to be these are indicators of the latent factors. And essentially, when I specify happy and mood 2, we're actually what we're actually computing is the covariance between the measurement errors for happy and mood 2. So it's not actually the happy and mood 2 variables directly. It's actually the error variances of happy and mood 2 are the measurement errors for happy and mood 2 that are being covaried. So that's the way to think about it. So with that, we then create, we're going to run our analysis. We're going to use the CFA function down here. And you can see that everything inside the parenthesis right here, these are various arguments with various specifications. And so we're going to be running our model, estimating the parameters and so forth. And then we're saving that information to an object that we're going to call fit. So that's why we have an arrow pointing to fit. So the fit name, that's just an arbitrary name that I typically use when I'm creating objects during the estimation process. And then we can use that fit object as an input into the summary function to be able to look at our results. So you'll notice that we've got right here inside the parenthesis. So again, CFA right here, that's our function. MM3 is the name of our object that contains the model. Then, excuse me, a comma, and then I've typed in sample.cov, and we're going to set that equal to covmat, which is the name of my covariance matrix. So keep in mind that if I was running my analysis from a data frame, instead of using the sample cov argument, we would be using the argument data, and we would set that equal to the name of the data frame. But because we're using summary data here, we can't use the data argument. What we use instead is the sample.cov argument. We set this equal to the covariance matrix, and there you go. So then I've got another comma, and then another unique argument when we're working with our summary data. We're going to type in sample.nobs. and we're going to set that equal to the sample size, basically, which is 263. That's the sample size that Kline used or describes in his book. So basically, these two arguments right here, if we were working with the raw data itself, we would not be using these arguments. We would be using the data argument and setting that equal to the name of the data frame that contains the data. So that's how to kind of understand the logic behind all this. So then we have this summary argument right here, and I'm going to refer inside of this to the fit object that I'm creating. So basically, I'm generating an object fit that contains information, and then I'm incorporating that as an argument in the summary function right here. And so from that, so our next step is basically going to be to have a comma, and then we'll have our next argument. I'm going to type in fit.measures and set that equal to true. So essentially, if I don't do this, if I don't request use this argument right here and set that equal to true, I'm not going to get as many fit indices as I would if I do set this equal to true. So I've added this fit.measures equals true. True is in caps, then a comma, and then I like to get the R-square values for my indicators, or or in the prediction model itself later on. So I'm going to type in R-square, set that equal to true, then a comma, and then if you want standardized coefficients in your output, then you can type in stand, set that equal to true right there. So what I'll go ahead and do is I'm going to highlight all of this. I'll even include the comment up there. We'll copy this and we'll paste it in and then hit enter. And so now we get our main output. So as we're looking at this, just kind of going through the output that you see right here, you'll notice that we've got the chi-square goodness of fit test that's presented up here. So this is the chi-square value, degrees of freedom for the model, and then the p-value. And so the chi-square goodness of fit test is a test of exact fit. So we're basically what we're trying to do is to determine if the covariance matrix that's implied by our model is adequate, basically does a good job of reproducing the sample covariance matrix. So in other words, we're just kind of looking to see if there's a difference between the sample covariance matrix and the model implied covariance matrix. And so if there's no difference as assessed by this chi-square goodness of fit test, then in that particular case, that would be an indication of good model fit, or at least we can't reject the exact fit hypothesis. The exact fit hypothesis is essentially the null hypothesis for that test. Then you'll notice that we've got the comparative fit index and the Tucker-Lewis index right here. So both of these values you can see are 0.991, 0.987, and these values have a theoretical range between 0 and 1, where values that are closer to 1 are basically signifying better fit. The general cutoffs that are typically discussed in literature, CFI or TLI values that fall 0.90 or above might be considered indicative of an acceptable fitting model. Values that fall above 0.95 would be kind of more optimal fit or superior fit of the model to the data. So next, what we'll do is we will kind of scroll down a little bit more and look at some other indices. So we've got down here, we've got the root mean square error of approximation, or the RMSEA right here. And you can see that we have this 0.028. So basically, in terms of interpreting the RMSEA, values that fall between 0 and 0.05 would be considered indicative of a close fit model fit to the data. Values that fall between about 0.05 to 0.08 would be regarded as acceptable fit. And then values that are above 0.10 would be considered poor fit. So you can kind of think about the values between 0.08 and 0.1 as kind of more mediocre fit. You also notice too that we've got the p-close test right here. This is basically testing whether the RMSEA that we have computed in our data right here, is this significantly different from what we would expect with a close fitting model. So the p-value that's printed out right here, the 0.936, that's actually not indicating non-significance. So that's actually a good thing. A non-significant p-close test would basically be indicating that we actually do have good fit. So the RMSEA and the p-close test, both of those are signifying good model fit. You also see too that we've got the RMSEA, this confidence interval for the RMSEA. And you can see that the lower bound is essentially 0. The upper bound is 0.052. So this is a fairly tight confidence interval, and essentially most of the values pretty much fall in the range of close fitting model. So the 0.052 may be a little bit higher than what we would consider close fit if we use a 0.05 as that threshold, but it's by and large suggesting a close fitting model to the data. Then finally, we've got the SRMR, the standardized root mean square residual down here. And this is the value of 0.037. And so basically values that fall between 0 and 0.05 indicate good model fit. Values from about 0.05 to 0.10 would be considered acceptable fit. So all of these indices are generally indicating good model fit to the data. So if we scroll down, we can take a look at our output right here. Just so you know, by default, Lavaan essentially is going to fix one path from each factor to an indicator variable to 1. So and so it's basically using what's referred to as a marker approach, or basically you're kind of setting a marker variable for that factor, and you're scaling that factor in relation to that marker or reference variable. So you can see right here that we've got a 1 right here. So with respect to this work 1 indicator, then down here with so that's with job satisfaction right there. Then you've got with this well-being latent variable, you've got this 1 right here for the factor loading involving the happy indicator right there. Then for dysfunctional thinking, you can see we have a 1. Basically a factor loading is fixed to 1 for the perform 1 variable that you see right here. And then for constructive thinking, you can see that we have this 1 right here for the beliefs indicator. So essentially, we're scaling the latent variables in relation to these marker variables. And then you'll notice there aren't any tests or anything like that associated with these fixed parameters, but we do have estimates, unstandardized factor loadings for the remaining indicators, and you can see that we have tests of them. So you can see that all of these are statistically significant. So that's a good thing. You also see too that because we had requested the standardized output, you can see that in this last column right here, we have what we have are basically standardized factor loadings. Okay, and so in our model, because basically each of our variables indicators are associated with a single factor, you can pretty much interpret all of these loadings right here as correlations between the indicators and their respective latent factor. And so there you go. And so at this point, we're going to kind of scroll down a little bit further and look at the covariance output. So you'll notice with the covariances output down here, we've got, it says happy, the 2 tildes mood right there. This is the covariance between the measurement errors, or the residuals for the happy and mood 2 indicators. And you can see that covariance is statistically significant. And this right here would be the correlation between the measurement errors for these 2 variables. Then you've got the covariances between job satisfaction and well-being, which is this right here. And you can see it's significant. Between job satisfaction and dysfunctional thinking, there's a negative covariance right there. It's significant. Between job satisfaction and constructive thinking right here, it's there it is, and you can see it's significant. Then in terms of well-being, we have the covariance between well-being and dysfunctional thinking. There's the covariance. It's significant. Between well-being and constructive thinking, positive, and this is actually non-significant using our conventional 0.05 threshold. And then the covariance between dysfunctional thinking and constructive thinking, there's the covariance, and you can see that's also non-significant. So, but still, if we go back and we look at this set of values right here, these would all be considered correlations among those latent factors. When we scroll down a little bit further, you can see in our output that we've got variance estimates. So you can see there's our variance estimates for work 1, work 2, work 3, and so forth. Usually we don't spend a whole lot of time in this particular area, but that's just basically what that information is. Sometimes, under certain circumstances, if it happens to be the case that you end up with a negative variance, that's actually not a good thing, and that could be a function of the model specification or characteristics of your data that's producing that negative variance. And so negative variances are generally not good, and when that's the case, then you can't really trust your results. But we're all good right here, and we'll kind of go down a little bit further and look at the R-square values. So the R-square values, you could just basically think of these as communalities, and essentially reflecting the proportion of variation in each of these indicators by the latent factors, or their respective latent factors, if you will. So there you go. The lowest R-square value is actually for the self-talk variable. That R-square is 0.188. Basically, its factor is accounting for about 18.8% of the variation in that indicator. The largest one is for this perform variable right here at 0.817 for the R-square value. So the next thing I'll show you is that if we use the SEM paths function associated with, go back to the SEM plot package, then basically we can just type in the name of our fit object, and I've typed in what equals, and inside the quotation marks I've got stand. So I'm going to actually be requesting standardized estimates in the figure that's going to be created. We have a comma followed by layout set equal to tree in quotation marks. So if I copy this and I paste this in, you can see a diagram of our confirmatory factor analysis model right here. So you can see that we have standardized loadings that are shown in the paths from the latent variables to their respective indicators. And any of the red that you see in this is basically a non-significant parameter, if you will, a test that's indicating non-significance. So that's kind of what you can see right there. And then the weights of these paths, like the thicker paths are indicating a stronger relationships, and then the thinner paths are reflecting kind of weaker relationships. So at any rate, that's just kind of a breakdown of that. There's more information in the documentation on using the SEM paths function, but I'm not going to go into all that. This is not really about that particular using the SEM plot package and those functions. This is just to kind of show you that you can generate figures in this kind of way. So next, we're going to go down and we're going to add the structural portion to our model. So I'm going to call this SM, just kind of referring to structural model. And you can see that inside between the single quotes right here and here at the very end, it doesn't really matter where I end it there, I have the entire model specification. So you'll notice that at the top, I've added a comment just to say I'm referring to the measurement portion of the model, and really that's going to cover all of this right here. So everything that I've typed in up to this point in the previously, I'm leaving that alone, and that includes this little comment for error variance and adding that error variance between happy and mood too. So I've added another comment for structural model, and then down below I've typed in job sat and a tilde followed by the constructive thinking plus well-being plus dysfunctional thinking variables. So I'm referring to making sure that I'm referring back to the factors that I have specified up here. So that's the specification of the relationships between job satisfaction and its predictors. So the predictors were constructive thinking, well-being, and dysfunctional thinking. Then on the next line, I've got well-being, tilde, and then dysfunctional thinking plus constructive thinking right there. And then on the last line, I've got dysfunctional thinking, tilde, constructive thinking. So basically in terms of the specification with the structural model, we're using the same way approach that we used if we're running a linear regression using the LM function in R. So it's just basically dependent variable tilde, independent variables separated by plus signs. So it's the same structure as that. So now we have specified, we have our model, it contains a measurement portion as well as a structural portion, making sure to have that in single quote right there. And so now we can run our analysis. So I'm going to create a new object. We'll call it, I'll just go ahead and call it fit2 actually. And so for all of these inputs into the summary function and SEM paths, I'll call it fit2 as well, just to distinguish it. A lot of times it's a good idea when you're running your analyses, you can kind of keep your results and everything separate in different objects. So I'm just going to call it fit2 just to kind of keep things a little bit separate. So now I'm going to highlight all of this. I'll even highlight the SEM paths down here, and I'll copy, and then I'll paste it in and run it. And so now you can see on the right, our figure shows up, which is good. You can see the non-significant parameters in that model. Going back up to the top here, you can see our chi-square goodness of fit test. You can see right here, it's indicating non-significance. There's our CFI and TLI right there, indicating good fit. When we scroll down, you can see it. We have our RMSEA and the P-close test. Both of those are indicating good fit, as well as the SRMR. Now, the thing is that really, to tell you the truth, the fit of this model is exactly the same as the fit of our measurement model. And that's because in terms of the number of parameters that are being estimated among the latent variables, they're exactly the same. And so our model is essentially just identified, or at least the latent variable portion of the model is just identified. So we don't have any change in fit as a result of adding in our structural relations, but we can still look at our output to test our predictions. So I'll scroll down and you can see that we've got, again, all of this is the measurement portion right here. When I scroll down a little bit further, you can see it says regressions. So I've got job satisfaction regressed onto constructive thinking. You can see there's our estimate right there. You can see it's not significant. This is our p-value for our test. This is also, by the way, would be our standardized regression coefficient or standardized path coefficient. Then we've got job satisfaction regress onto well-being. So there's our estimate. You can see that that well-being is a significant positive predictor of job satisfaction. There's our standardized estimate as well. In terms of dysfunctional thinking as a predictor of job satisfaction, it's a negative predictor, but it's not statistically significant at the conventional 0.05 level. When we look at well-being in terms of its predictors, we've got dysfunctional thinking. There's a negative predictive relationship, and you can see that relationship is significant. For constructive thinking in relation to well-being, positive but not statistically significant. And then looking at constructive thinking as a predictor of dysfunctional thinking, you can see that we have a negative coefficient, but it's not statistically significant. In terms of the covariance between the happy and mood variables, there's our covariance estimate right there, and significant. In terms of the R-square values, not only now do we have the R-squares associated with the indicator variables, which essentially is all of this stuff right here, these R-squares. But now we've got R-squares for our structural portion of our model. So in terms of the predictors of job satisfaction, they account for about 24.5% of the variation in job satisfaction. In terms of well-being, as the endogenous latent variable, its predictors account for about roughly 24% of the variation in that. And then in terms of dysfunctional thinking, there was only constructive thinking that was a predictor in the model. So that constructive thinking only accounts for about 1.5% of the variation in dysfunctional thinking. So for the final model that's described on page 346 in Kline's book, he basically removes a couple of paths. So I'm just going to kind of show you, this is essentially the final model after removing a couple of the structural relations that were proposed. And then we'll see the difference in the fit statistics as a result. So for this one right here, I'll just call this SM2 instead of model. And so we'll refer to that. I'll call the fit object, I'll call it fit 3. And then we'll, again, we'll call this SM2. Now, note too that as you're looking at this, as I was going through, I was running the measurement model is testing with the CFA function right here. For the structural model, I was basically using the SEM function as well. And I'm going to use the same function right here for this third model. There's also, another function is called the Lavaan function, and so some of these different functions, they kind of differ in terms of what some of the defaults are or whatever. And so I would recommend that you still check out the documentation on these functions to kind of get a better picture about, what those defaults are, and then you can kind of strategize about which way you want to go in terms of their use. But so we're using the SEM function right here, and because I'm just naming this next model SM2 right here, and so we're using that as an input right here. We're still using the same sample covariance matrix, the same number of observations. We're going to use the summary function. We're going to input the fit3 fit object. So this object that we're going to create right here, and we're still going to use the same arguments, set equal to true in terms of fit.measures and R square, and stand set that equal to true. And then down below, we're going to with our SEM paths function, we're going to use the same thing. So I'm going to copy this and paste it into our RStudio here and hit enter. And so now you can see we have the diagram of the structural relations and the measurement portion as before. So if I kind of bring this out, you can see things a little bit closer. You can see, just basically all these different aspects. You can see too the red is denoting non-significant relationships. So going back and looking at the overall fit of the model, now you can see that in terms of the goodness of fit test, the chi-square goodness of fit test, you can see that this is still statistically non-significant, or it's non-significant. So that's, again, we can't reject the exact fit null hypothesis. So that's actually a good thing. In terms of the CFI and TLI, both of those are still very close to 1 and indicating good model fit. When we scroll down and we look at the RMSEA down here, you can see that the value is 0.029. The P-close test is also, both of these are indicating good fit. You can see our confidence interval is still nice, pretty narrow, and still largely falls within the close fit range. And then our SRMR, you can see it is still indicating a good model fit. So going down and looking again, we've got, just to reiterate, this is the measurement portion of our model. And then with respect to the regressions, you can see that in terms of job satisfaction, this endogenous latent variable, this being predicted by well-being and dysfunctional thinking, you can see that well-being is a significant positive predictor of job satisfaction. Dysfunctional thinking is a significant negative predictor of job satisfaction. In terms of predicting well-being from dysfunctional thinking, we've got our negative regression slope, so that's a negative predictor, and we have statistical significance. In terms of constructive thinking in relation to dysfunctional thinking, we still have the negative regression slope right here, and it's still not statistically significant at the conventional 0.05 level. In terms of the covariances, between the covariance between the residuals for happy and mood, still negative and statistically significant. So in terms of looking at our R-square value, in terms of our three endogenous latent variables right here, job satisfaction, you can see basically the predictors of job satisfaction in this last model account for about 24% of the variation. In terms of well-being, its predictors are accounting for about 23% of the variation. And then again, with that last, with dysfunctional thinking, constructive thinking is not accounting for really much variation. It's only accounting for about 1.8% of the variation in dysfunctional thinking. So that's basically a general overview of how to test a full structural equation model using Lavaan, and we're also carrying this analysis out in RStudio. And what I'm going to do is include a link to the syntax or the text file that I have just been walking through underneath the video description, so you can download a copy of that and kind of learn more about the structure of that syntax, and you can actually copy and paste into RStudio, and you'd be able to should be able to replicate the same analyses. Just to reiterate, if you haven't already done so though, you need to make sure that you have Lavaan and SEMplot installed in order to be able to use them. So I'm just reiterating that point. So that's going to conclude this video presentation, and I appreciate you watching.